Welcome back to another fun edition of online math. First, I want you guys to go ahead and check your answers to the warm-up problems. Make sure you were able to identify the midline, the amplitude, the period, and then write either a sine or cosine function to represent the graph. I only have one answer written for each, but there are multiple answers. Keep that in mind. Once you're done checking your answers, we're going to go ahead and get started on the worksheet today. So last time Mr. Jolly spoke to you about amplitude of a function, and then he also spoke a little bit about b values and how they end up changing the period of the function. Today what we're specifically talking about is right down here. It's called phase shifts. Okay, so the first thing I'm going to ask you to do today is write one sine function, gotta highlight that in blue, and one cosine function to represent the graph below. So the trick here is I'm going to write one function, two different equations, but they're both going to represent the exact same graph. Starting with sine, I think that makes more sense for me because we can see that we're starting at the point 0, 0, which we know is a good sine function start value. Then it goes up to the maximum, back to 0, down to the minimum, back to 0. And that's the 5 points. We always want to talk about those 5 key points to identify one period of the function. And we can tell where one period is. It's when we're going up through the x-axis, back to where we're going up through the x-axis again. And those 2 points are 2 pi apart. So that's what represents the period of our function. Okay, then we need to identify the amplitude. The amplitude goes up to +1, down to -1. So the amplitude is going to be 1. The amplitude is never a negative value. Okay, it's always going to be a positive number. It's important to remember that. Even if there's a negative in front of the sign, that might represent a reflection, not an amplitude of a negative value. The last thing we notice here is that the midline is perfectly at y equals 0, or d equals 0. So this one's not shifted up or down at all. So we're going to end up with a function here, amplitude of 1. This is just a simple y equals sine of x, since the period's 2 pi, which is normal for these types of functions. Now, we can also write a cosine function for this exact same graph. Things that are going to be happening with the cosine function, though, when we're looking at this instead, is we're going to see this goes from peak to peak. So there's the first point there, second point, then we go to the minimum, back to 0, and then to the final maximum. So cosine functions typically start at the maximum value and then go over. So we can see that this maximum value is starting at pi over 2. So that's what's happening here. We're seeing that this thing is shifted pi over 2 units. The cosine function is going to have the exact same amplitude, same midline, same period. The only difference is there's a slight shift. So we'll see cosine of x, since we're shifting to the right, pi over 2 units, we say minus pi over 2. And this represents a phase shift. That's what we're going to be talking about today. Phase shifts. So one thing we can say that's true about parent functions, if we have sine of x, we can say that's the exact same thing as cosine of x minus pi over 2. We can just shift to the right pi over 2 units, and then we're going to end up with that cosine function. And likewise, if we start with a cosine function, you can actually shift that one to get the sine function, except in this case you would shift to the left pi over 2 units to get back to the sine function, which I'll show up here. There's that shifting left if the cosine started at 0 instead. Now we can talk about these two parent equations. There's going to be y equals a times sine of b, and then x plus c plus d. That's what this thing is going to look like. And notice we're going to put the b outside of the parentheses. That's really important to note. When we talk about cosine, the equation is going to generally look like the same thing, except we're going to have a cosine instead. So last time Mr. Jolly spoke with you guys about the a, the b, and the d values. The one that we skipped was the c value. That's the phase shift that's taking place. So the phase shift is always going to be represented by a horizontal translation. So we're going to highlight those real quick. Okay. That is a horizontal translation of -c. All right, that's exactly what's going on here. Our first example today, asking you to sketch a function for f of x equals sine of 2x plus 2 pi over 3. The one small issue here is that we see that the function is not written in the b times x plus c form that we just spoke about. So what we're going to need to do is we're going to need to undo the distributive property basically. We're going to need to pull that 2 out. And that's what we need to talk about here. So I can rewrite this equation as sine of 2x, and then I have to think about this was a 2 pi over 3. So I need to do something times 2 to get to 2 pi over 3. Technically, it's just going to be a pi over 3. And that's where this is going to change just a little bit. And we can see if I use the distributive property, I'd get 2x and then times pi over 3. That would give me 2 pi over 3, which is the exact same thing. That's what I want to see. So these are the same equation, but when I rewrite it a certain way, now I can clearly see a b value, and I can clearly see a c value right there, the positive pi over 3. So if b equals 2, what's the period? And this is where we talked about it last time. We would need to say, oh, that's going to be 2 pi over b. Or in this case, 2 pi over 2, and 2 divided by 2 is just going to be pi. So the period is just pi. All right, so now I know this function is going to go from 0 to pi. If I were just to sketch the function, just do a quick sketch, I'm probably going to want to do just one period of it. It doesn't give me a specific interval to do this on. And I'm going to start at, let's see, 0. It's a sine function. I'm going to go up to my maximum, back to 0, to my minimum, back to 0. And I know this thing's ending at pi. So then it's going to be halfway between 0 and pi is pi over 2. Halfway between 1/2 pi and 0 is 1/4 pi. And then halfway between half pi and 1 pi is 3 pi over 4. Basically, we're doing this by fractions. I'm going 0/4, 1/4, 2/4, which is really 1/2, 3/4, and 4/4, which simplifies to 1. Then I can sketch my graph. Okay, now that's what this graph looks like, but this is with just the period, but without the phase shift. So I need to sketch one more time with the phase shift. So this is without phase shift. Now, with this plus pi over 3, that means I want to move everything to the left pi over 3. Move that point, pi over 3. Move that point, pi over 3. Move that point, pi over 3 to the left. And then finally the last one, pi over 3. Well, the 0 is going to be easy, because if I'm moving the 0 over, that's just going to start at negative pi over 3. That's the easiest one. The next ones are not going to be as easy. Pi might not be too bad because you're going to subtract pi over 3, so this is going to end at 2 pi over 3. So we know where it's starting and ending. But the other three values are going to be kind of tricky. I have to do pi over 4 minus pi over 3. 1/4 minus 1/3. So we have to be really good at fractions here. Maybe you can use your calculator to do that. 1/4 minus 1/3. Plug that into your calculator and see what you come up with. What's really going to happen is we're going to have 3/12 minus 4/12, which is really negative 1/12. But we're also dealing with those pi's, so it's going to be negative pi over 12. And that's going to be our maximum value here when we get to 1. And then our minimum value is a negative 1. If we do the same thing with pi over 2, that's 6 pi over 12. And we subtract 4 pi over 12, we're going to get 2 pi over 12, or that's a positive pi over 3. That's going to be the next 0 value. And then the last one, 3 pi over 4. If we turn that into 12, that's 9 pi over 12. And we're going to subtract 4 pi over 12. We're going to end up with 5 pi over 12. And that's like our minimum value here at -1. Oh, that's not the prettiest sketch. But that's kind of what this is going to look like for one period of the function, since I wasn't given a specific interval in which to graph the function on. And that's a tricky problem. We have to be able to first remove that 2, so that way we can see this in the b and then quantity x plus c form. So that way we can identify the period of the function, and then I sketched that, and then I dealt with the phase shift after that. That might be the easiest way to deal with this type of problem. Let's look at one more example now. Okay, so our next example says the graph of the function in the form y equals a cosine bx is given in the diagram on the right. Write down the value of a, right, and then calculate the value of b. So for a, we're just going to go from max to min. We're seeing we're going from 14 to -14. That's a total of 28. The amplitude is always half of that. So we would say a equals 28 over 2. Or just 14. So a equals 14. The b value, we have to find that out from the period of the function. So we can see this thing's going one period from 0 to pi over 4. That's where it ends. So one period is pi over 4. And now that we know the period is pi over 4, we can say, okay, well, 2 pi over b equals pi over 4. Technically, I don't want to multiply both sides by 4 over pi. That's going to get that to the other side of the equation for me. So I'm going to end up with this side is going to be pi over 4. That just becomes a 1. The left side of the equation becomes 8 over b. And then I can multiply both sides by b, and I end up getting b equals 8. So that's how I would solve that type of example using a graph. So if I give you a graph, we should be able to find the amplitude, find the b value, find the period of the function, all of those types of things just by looking at it. We'll also get better practice at looking at phase changes, phase shifts, as well as midlines, equations of midlines. Okay, last example today is going to ask us to do a couple things. It says first, for the function f of x equals 2 cosine of quantity x over 2 minus 3/2. So let's identify our values. We've got a value is 2. The b value here is 1/2. Their c value is 0. There's no phase shift. That's kind of nice. And then the equation of the midline is going to be at -3/2. Important note, we're going to sketch this function on the interval from -pi to 5 pi. Starting with the b value of 1/2, we'll go ahead and do this in red. I know the period of the function is going to be 2 pi over 1/2 equals our period. And for this one, whenever I have a fraction over another fraction like this, I can really say 2 pi times 2 over 1. Flip the bottom fraction, the reciprocal of the fraction, to find the period. So 2 pi times 2 is 4 pi. So that's our period of the function. Okay. Now we've got the amplitude is 2. We know where the midline is going to be, and we know the period of the function. This is also a cosine function. Since I know it's a cosine function, I know it's going to start at wherever my midline is. So if I were to sketch 0 here, my midline is going to be at -3/2. I'm going to go up 2 from that. So up 2 is to +1/2. That's where this one's going to start at 0. And it has to go back to -pi. It has to go all the way up to 5 pi. There's pi, 2 pi, 3 pi, 4 pi, 5 pi. One period of this function is 4 pi. So I know it's going to hit the maximum at 4 pi again. It won't hit the maximum until then. And that's kind of nice because it makes our 5 points pretty easy, because we go halfway between 0 and 2 pi, or 4 pi is 2 pi. And then halfway between 2 pi and 0 is pi. We always want to split this thing into fourths once we find the end of the period. And then halfway between 2 pi and 4 pi is 3 pi. So now I know that this is going to go all the way up to 1/2, and it's going to go down 2 from 3/2, which is going to be down 1 is -5/2, down 2 is -7/2. So this will go all the way down to 7/2 by there. And the 0 value is going to be where the midline is. I'll sketch the midline here. And I know 3 pi is also going to be at that 0 value. When I get to 5 pi, it should be back down to the 0 value. And when I go back to -pi, it should also be back down to the 0 value. So now I can go ahead and sketch this graph. And when I sketch it, very important to remember, we draw arrows at the end to represent, hey, this function is going to keep going on. We're just sketching along this interval from -pi to 5 pi. That's very important. When we get to the domain and range of this particular function, that's what part B is going to ask us for. Well, the domain of any of these functions is going to be all real numbers. That's what the arrows are for, saying, hey, this goes on forever. So we can write it in this notation as all real numbers, or we can write the domain in interval notation that says we're going from -infinity to +infinity. Both of those answers are correct. You can write either one. The range of this function is just going from the minimum value to the maximum value. In this case, we're going from -7/2, and we're including that value is less than or equal to y is less than or equal to +1/2. Or we could draw the range as -7/2 in interval notation to 1/2 in interval notation, and we do the closed brackets saying we're including those numbers in our range. The last part here is write f of x as a trigonometric function in terms of sine rather than cosine. All right, so that means we're going to need to do some type of phase shift here. So I can see where the midline is. We're going to keep that exact same midline value. So it's going to be -3/2. Whoops. I'll erase that. Let's say -3/2 there. And then we're going to have the same amplitude. And we're going to have the same b value of the 1/2. We're also going to have the same b value of 1/2. So what we need to do then is we just need to figure out the phase shift. So I can see if I look at this, if I want a positive sine function, I just need to shift to the left pi units. So I can write this down as y equals 2 times sine. This is the important part here. I have to write 1/2 and then in parentheses put x plus pi. Close those parentheses, and then I'm going to say -3/2. Really important that I write this as the 1/2 first and then the x plus pi. And that's because I can identify my b value and I can identify my phase shift. Technically, this is not simplified. In order to simplify this, we would need to do a little distributive property, and we would distribute the 1/2 here and here. And we can rewrite that function as y equals 2 times sine of 1/2 x plus pi over 2 minus 3/2. So once we distribute down to one set of parentheses, it's simplified. We could technically also write this as x over 2 instead of 1/2 x. A couple different ways you could write that. So it looks more like the original function above, but then we have that plus pi over 2. Even though there's not a phase shift of pi over 2 units to the left, it's actually pi units to the left. We can't tell that from this equation at the end. But this would be the most simplified equation when we're done. We could end up with some other equations because we could shift to the right instead, like we could shift pi units to the right, or we could shift 3 pi units to the right. If we shifted pi units to the right, that means this is going to be a negative instead. It's going to show a reflection. But we can do the same thing where we do 1/2 x and then minus pi, because we're going to the right instead, minus 3/2. Another way I could write it, y equals 2 sine of 1/2 x minus 3 pi minus 3/2. So a couple different ways to write it there. And that should cover everything from today. Make sure you guys get the assignment completed. Let me know if you have any questions. Make sure to come to office hours.